All right, what I'd like to do is a fairly short video now, going over a few concepts before we get to the line of best fit or prediction. So I'd like just to go back to the slides. I'm going to pick up on slide number 30. And again, if you have your packet near you, I think that would be very helpful. Here's something you want to go to sleep tonight with kind of memorizing, and that is correlation does not equal causation. I'll say it again. Correlation does not equal causation. So when you have a high Pearson product moment correlation coefficient in the range of negative 0.8, negative 0.9, or 0.8 or 0.9, it does not necessarily indicate that the two variables are in a cause and effect relationship. You cannot say that. Certainly you can make the case for causation by showing a strong correlation, but a lot of other things need to be in place in order for us to assume causation. One of the great examples of this is if we look at shoe size. Shoe size is correlated to intelligence. So my question would be, does shoe size cause us to be more intelligent, having a larger shoe size? No way. So there's really, in this particular instance, a third variable which explains what's going on. We find that as you get older, shoe size tends to increase. As you get older, you become more intelligent as you learn more. So there's a third variable of age that really explains this relationship. So this is a great example where correlation does not equal causation. Shoe size is related to intelligence, but it's really age is a third variable which explains what's going on here, and there's not a cause and effect relationship between these two variables. A second concept that I want to explore in this little video is what is called the coefficient of determination. You want to memorize this as well. The coefficient of determination is the R squared. So you take the correlation coefficient and you square it. That will give you the R squared, which is the coefficient of determination. The coefficient of determination is the proportion of variance or variability in one measure that can be explained by another measure. So I'm going to use this term variance a lot, and I'm going to remind you that variance is a term that indicates the spread, how spread out the scores are. And in this case, what we call the coefficient of determination, or the R squared, is going to indicate the proportion of variability or variance in one measure that can be explained by the other measure. So, for example, if we had a Pearson R of 0.60, we take that in our calculators, we square it, we find that the coefficient of determination is 0.36, and the way we interpret this is that 36% of the variance in our y variable can be explained by x. So there's a lot of variability in our outcome variable. Isn't it great if we could, isn't it great, or wouldn't it be great if we could explain a large percent of the variability in that outcome or y variable by our x variable? So that's the concept of the coefficient of determination. It deals with what we call the explained variance. So help me on this one. Here we have a correlation, which is a strong inverse correlation of 0.90. What is the coefficient of determination? The coefficient of determination is the R squared. You put this into your calculator, you square it, and you find out that the R squared is 0.81. What that means now is that 81% of the variability or the spread or the variance in y can be explained by the scores that we have on our x variable. 81% of the variance in y can be explained by our x scores. So R squared, again, is the proportion of variance in y that can be explained by x. I hope you figured out at this point that the R squared, no matter what the R is always going to range between 0 and 1. If we had a correlation, as we did in the previous slide, of R equals negative 0.9, the R squared is going to be 0.81 or 81%. So that gives us the proportion of variance in y explained by x. If we now take that R squared and subtract it from 1, we're going to find the proportion of variance in y that is not explained by x. Please, on this slide, in your notes, indicate that 1 minus R squared is unexplained variance, or what I will call error. So please write error next to this. Unexplained variance is error, and that's indicated by 1 minus R squared, or 1 minus the coefficient of determination. Generally, the plan here that we want to be thinking about as we move ahead in these slides is that we do want to explain things. We don't want much unexplained variance. We don't want much error. So I'm going to illustrate this graphically to you, or in a picture. Scientists often use what's called a Venn diagram to express this concept of the coefficient of determination, or R squared. And what happens here is we're looking at explained variance. We're looking at what is called shared variance between two different variables. In this case, this Venn diagram indicates that A and the variability in all of the A scores is indicated by this circle. So some people score over here, some people score over here, some people score over here, some people score over here. The variance, or the variability, or the spread on the B scores can be illustrated by this second circle. Some people score here, some here, some here. The shared variance, this is the explained variance, is what is illustrated by this overlap area. And one of the examples that I pulled for you was between whales and fish. Whales, there's all different kind of whales, and they're all over the place in terms of their different attributes. But we know that whales live in water, they have fins, they can swim, they have hair, they have live births, etc. They're variable, whales are all over the place, all right? But part of this variability in whales can be explained by, or has shared variance with some of the characteristics that we see in fish. For example, both fish and whales live in water. Both fish and whales have fins and can swim. So this is what we call the shared variance. This is the explained or overlap variance, and it indicates the percentage of variance in one variable that can be explained by the other. And that's the way we want to think of this concept of the coefficient of determination. Please take some time, review, understand the correlation coefficient, and all of the concepts that we've gone through so far. What I'd like to do now is take us back to our handout packet, and for this I'll bring us back to the top of page 6. And I want to let you know that your book does a very poor job of going into any kind of detail on a concept that I've asked that you memorize, and that is correlation does not equal causality. Correlation does not equal causality. In order for something to be causal, a number of different criteria need to be satisfied, one of which is there needs to be a strong correlation or association between the variables. But that alone is not enough to assume causality. So, for instance, the cigarette smoking cancer link. Many of the cigarette manufacturers for years were fighting this idea that, hey, how can you say for sure that cigarettes cause cancer? Yes, there's a high or strong association between the number of cigarettes that you smoke and your likelihood of getting cancer, but can you really say that one causes the other? So let's look for a minute here, and let's look at some of these other criteria of causation. One of them is what we call the dose-response effect. That is, in order for something to cause something, you have to know that there is an association between how much of the dose of the causal factor you get and how much of a response or an outcome that you get. In fact, it's pretty clear that if you get a low dose of cigarettes, meaning you only smoke 1 cigarette per day, that you have less likelihood of getting lung cancer than compared with the person who smokes 20 cigarettes a day, who's going to be much more likely to get lung cancer. So there needs to be this dose response effect in place if we're going to assume causality. This next one is extremely important and is one I oftentimes use as an example on exams. So please make sure you understand this word temporal. It means time. If something causes something, the causal factor should precede the outcome or the response in time. So there needs to be a lack of temporal ambiguity. We need to be sure if something is causal that the cause occurred before the effect. That's, in essence, a lack of temporal ambiguity. We are sure that the causal thing, in fact, came before the effect. Now, we also need to look across all of the research studies, and there should be a high degree of consistency of findings on all of the studies that have looked, for example, at smoking and lung cancer. Are they pretty much all showing that there is some type of association or relationship between smoking and cancer, lung cancer, before we say that it's causal? Also, if something is causal, there really needs to be biological and theoretical plausibility. That's a fancy way of saying there needs to have a mechanism that makes sense. Maybe some of the chemicals that are in cigarette smoke alter some of the DNA, alter some of our immune capabilities such that cancer cells are able to proliferate. There needs to be a biological, theoretical, rational reason why something should cause something. And so is there a mechanism? That also is an important criteria that needs to be in place before we assume causality. Across all kinds of evidence and facts, we need to have coherence of the evidence. All the arrows need to be pointing in the same direction, that smoking, in fact, causes lung cancer. And lastly, but certainly one of the most important criteria of causality, means there needs to be what we call specificity of the association. There can't be a third variable that could explain what is going on. The greatest example of that is the example I gave before of shoe size and intelligence. Maybe the third variable in that case is age that is really the driving factor. So please make sure you familiarize yourself with these criteria of causation. Correlation does not equal causality, although it is part, if you look on my slide here, it is part of making the case that something causes something. The last concept in this unit, again, is the coefficient of determination, or the R squared. Here's another one of these Venn diagrams. Here we have pictured our IV, which you should label your X variable. Your dV is your Y variable. This is the presumed cause, or the predictor. This is the outcome, or your dependent variable. And the degree of overlap is given by the coefficient of determination. In this case, the R was 0.30. We square it. We find that the coefficient of determination is 0.09. And we say that 9% of the variance, or the variability in this Y variable, can be explained by this X variable. So R squared is the ratio of explained variation or explained variance to the total variance. If this was our R squared is 0.85. It means 85% of the total variation in Y can be explained by the relationship between X and Y. This is a little bit more detail. The other 15% of this is unexplained variance. I want you to know that unexplained variance is what we call residual, or what we call error. It's bad. We don't want it. We want to explain things. And one way of saying this is when we look at the relationship between two different variables, we want the R to be high. We want the R to be high or strong. And number two, we want the R squared to be high. We want the coefficient of determination to be high so that we can explain variability, so that we can explain variance. Unlike the correlation coefficient, which can range from -1 to 1, the R squared is going to range between 0 and 1. So make sure you have that down and that you understand that. Okay, I'm actually going to stop this here and allow